Welcome to another lecture on the topic of graphing rational functions. We want to examine the graphs of three rational functions. The first one is y equals x squared minus 4 over x minus 2. The numerator is a quadratic function. The denominator is a linear function. Now, perhaps based on habit, in order to find the equation of the vertical asymptote, very quickly we set the denominator equal to 0. So here, if we do that, if we set the denominator equal to 0, we may have this impression that x equals 2 is the equation of the vertical asymptote. But this is like an immature approach because we have to always be careful about the existence of holes in graphs of rational functions. If you look at the numerator can be factored as x minus 2 times x plus 2. And when you simplify x minus 2 from top and bottom, you end up with actually y equals x plus 2. And x plus 2 is nothing but a straight line. Of course, it's a straight line with a positive slope of 1 rising from left to right. So if I draw that line, it's going to be a line like this. It's a straight line with a positive slope, and it is rising from left to right. And that's how the graph is going to look like. Now, the thing is that at x equals 2, we just want to know what is happening. Well, at x equals 2, the numerator becomes 0 because x minus 2 is a factor of the numerator, x squared minus 4, and we have x minus 2 in the bottom, so if x is 2, we have 0 over 0, which is called indeterminate form in mathematics. So we cannot have any value for the function if x equals 2. In other words, at x equals 2, nobody knows what is the value of the function. So in that case, we say that at x equals 2, we have a hole. So I'm going to draw a hole like this. It's an empty circle. And we say that this function has a hole at x equals 2. So saying that x equals 2 is the equation of the vertical asymptote is a very, very incorrect thing for this function. So we should not always blindly set the denominator equal to 0, quickly find the equation of the vertical asymptote and announce it. We have to check to see if the factor in the denominator is a common factor in the numerator or not. If we have a situation like this, then we have a hole at x equals 2, and we do not, I repeat, do not have a vertical asymptote of x equals 2. And as you see, the graph of this rational function is like a straight line rising from left to right. It doesn't even have a vertical asymptote. So I'm going to label this graph. I was going to say this is like x squared minus 4 over x minus 2. This is the graph of this rational function with no vertical asymptote actually. And then for this second one, the numerator is quadratic, the denominator is linear. So in this case, if you examine x plus 1 does not have any factor in the numerator, because in fact the numerator is a quadratic binomial that is not even factorable, let alone having x plus 1 as its factor. So that's not the case that we had before. So here, freely, with 100% accuracy, I can say that x equals negative 1 is the equation of the vertical asymptote. So I can draw x equals negative 1, and I can claim that this is actually the vertical asymptote. But then the degree at the top is 1 more than the degree at the bottom. Therefore, we do not have any horizontal asymptote. So I'm going to say no horizontal asymptote. But instead, we do have a slant asymptote or oblique asymptote. Now, the question is, how do you find the equation of this oblique asymptote? Well, the shortest, the easiest way of finding this slant asymptote is by using long division. So I'm going to divide the numerator by the denominator, and I'm going to use the process of long division. So x squared divided by x is x, so I get x squared plus x. And then when you subtract, these two cancel out each other, you get negative x plus 4. And then when you divide negative x by x, you get negative 1. Multiply, negative x minus 1. And when you subtract, these two cancel out each other, 4 minus 1 becomes 5, the remainder. Now, we look at the quotient that we get from the process of long division. Whatever the quotient is, y equals that quotient is automatically the equation of the slant asymptote. So it's that easy, straightforward procedure to find the equation of the slant asymptote. So we're going to say slant asymptote. The equation is y equals whatever the quotient is. You found x minus 1, so y equals x minus 1. And it's always in the form of mx plus b, obviously. So y equals x minus 1 is a slant line, straight line with an x-intercept of 1, y-intercept of -1, and it is rising from left to right. The slope is 1, so you can easily draw that. And then, just like before, you're going to perform an analysis for the behavior of the graph at the neighborhood of its vertical asymptote. And also, we can perform intercept analysis and all those steps we had in the past. For example, the y-intercept here, if you set x equal to 0, you get 4 over 1. So the y-intercept is 4. We know exactly where the graph intersects the y-axis. And when you try to set y equal to 0 instead, you get x squared plus 4 equals 0, which is impossible. The equation has no real roots because x squared plus 4 is an always positive expression regardless of the value of x. So that means that we do not have any x-intercepts, and that means that the graph does not intersect the x-axis. It only intersects the y-axis. So the graph starts from the right-hand side of the vertical asymptote. It decreases, crosses the y-axis at the y-intercept, and then it approaches its slant asymptote on the right-hand side. And the other branch is very similar to this one. Again, the graph starts increasing, and then it approaches negative infinity on the left-hand side of the vertical asymptote, whose equation is x equals -1. So that's how the graph of this rational function looks like. Now, you can perform the analysis of behavior of the graph at a neighborhood of its vertical asymptote by yourselves, as we have done in the past. You see the domain of function. Domain of the function, again, is all real numbers except the root of the denominator. So you can say all real numbers except x cannot equal to -1. In this case, we could say the domain is, of course, the set of real numbers except x cannot equal to, of course, 2, because at 2 we discussed that we did have a hole. In this case, we did not have any hole at all. In the third example, the top and bottom are both quadratic. So the first example, quadratic linear, quadratic in the top, linear in the bottom, with a hole. This one was quadratic in the top, linear in the bottom, without a hole, with a vertical asymptote. And now this one, we have quadratic in the top, quadratic in the bottom, and we don't even know what's going to happen. So in this case, we'll try to factor the top and bottom and see what happens. If you factor the numerator, I think you get y equals 2 numbers add up to 1 with a product of -12. I believe it's x plus 4 and x minus 3, and the denominator would be x plus 4 times x plus 2. Okay, 2 times 4 is 8. So now, when you factor the top and bottom, you notice that x plus 4 is a factor that is common in the numerator and the denominator. It reminds me of this first exercise where x minus 2 was common. So this means that at x equals -4, which is actually one of the roots of the denominator, we do have a hole. So at x equals -4, we do have a hole. And we cannot say x equals -4 is a vertical asymptote. But the other factor, x plus 2, will give us x equals -2 as the equation of the vertical asymptote. So here I can say x equals -2 is the equation of the vertical asymptote, because that's one of the roots of the denominator. And then I would say we have a hole at x equals -4, okay? And regarding the horizontal asymptote, well, I can say the ratio of the leading coefficients is 1, so it's going to be y equals 1, so that's the horizontal asymptote. And when we do have horizontal asymptote, we do not have slant asymptote. So I'm going to say slant asymptote, we have actually none. So this is the story of this rational function. And obviously, if you simplify x plus 4, they cancel out each other. You get x minus 3 and x over x plus 2 in the denominator. So that's how the graph will look like in this case. And if you want to draw the sketch of this, again, performing an intercept analysis, if x is 0, you get negative 12 over 8, which is actually negative 1.5. So the graph looks like something do we have an x-intercept? Yes, the x-intercept is 3 actually. So the x-intercept is right there. The y-intercept is at negative 1.5. This is negative 1.5. So the graph is going to look like something like this. Okay, and the other branch would be something like this. So that's how the graph will look like on either side. Again, just like in the past, you can perform an analysis for the behavior of the graph at the vicinity of its vertical asymptote x equals negative 2 to figure out if y approaches positive infinity or negative infinity on the left-hand side or right-hand side of the vertical asymptote. So we talked about all the asymptotes. Now we forgot one last thing, the most important thing, the hole actually. At negative 4, we said that we have a hole. So here, x equals negative 4 is right here. So I would say at this point, we're going to have a hole, which means that the function is not defined at x equals negative 4. And this is how the branch would look like. The other branch on the right-hand side is okay. So here we do not have any hole. So everything is fine. All the points are defined, but not here. So we have a hole right here, okay, at x equals negative 4. And obviously that's because of the factor that is common in between the numerator and the denominator. So I hope you understood the difference between vertical asymptote and the hole in this lecture. So sometimes we have a hole only, sometimes we have a hole and we have a vertical asymptote, and sometimes we have only vertical asymptotes without any hole. I hope these 3 examples clarifies all the details involved with the curve sketching of rational functions. Thank you for your attention and keep practicing.